Hey, year 13s, thanks for coming, guys. Sorry I'm a little bit late. It's a quick lesson today, though, which is nice. So today is A2 Thermodynamics Lesson 4, and we're doing solutions, so enthalpy of solutions. So I will share my screen. I have 3 people in the class with me who I'm going to be asking all the questions to. I get to bully them today. It was amazing. Love it. Okay, so straight away here with my learning objectives, folks. There you go. So you guys just need this. It won't be working for you guys because you're in school and the school block it. But it should. Can I ask a favor? Can I ask my students who are currently watching YouTube, can you post on the chat, please? Just to make sure, just so I know that it is actually functioning. That would be grand. Oh, terrible quality on the sound. Try and reduce my voice a little bit. Speak, no, it's not what why have I just swapped over to that? Microphone? Don't know. Oh, so Ivan's in there. I'll pop out the chat, so at least I can have that there. But in reality, I'm not going to be able to use the chat today because you guys are going to be watching the screen, so we'll get rid of that. But just let me know that it's working on YouTube. Okay, so 3 learning objectives: understand hydration versus solution, be able to draw cycles, and know endo and exo dissolving processes. Just to know a couple of them, a couple of the examples where you see these. Really, it's about focusing on the endo ones and explaining why the endos ones exist. Okay, sorry guys, that's my cable causing me a bit of trouble there. Okay, so it'll come back on in a sec, folks. It will. It's my the laptop. I'm not gonna lie, is a bit rubbish on in terms of connections wise. Come on, it's now gone completely to sleep. Try that, and it should come back. Come on. Come on. What's going on here? This is the problem with rubbish cables. Why is it gone to sleep like that? Projector's no longer working. What? I couldn't use the Google Meet, the Google Chromecast. It's now no longer working on the projector. What is that about? Oh. No, let's try the other way. So it appears that the cable wants me to hold it up. Let's just shove something. There we go, it'll work now, watch. There we go. Right. Okay, first of all, let's do some definitions. So and equations. So let's talk about solution first. Delta H solve. So this process, the enthalpy change, the heat energy change, when 1 mole of an ionic compound is dissolved in excess water forming aqueous ions, all under standard conditions. You don't need standard states here. Yeah, standard conditions, of course, is constant pressure. Equation, NaCl solid going into water, excess water, to form Na plus aqueous and Cl minus aqueous. We know this. We've been seeing that equation for dissolving since year 10 was the first time we will have seen this. Now, it's interesting to say the excess water. Now, would that, any reason why you think you need to say excess water? Simplify it. There's something simpler that you come across in year 7 that is playing a part here. Well done, thank you very much. We know that different salts have different solubilities. So if I was going to do this process and I had a salt which was low in solubility, I'm going to need a vast amount of water to be able to dissolve it into. Does that make sense? These questions every now and again do appear. There always a suggest one too. They're tricky. Okay, so we understand that the dissolving process is adding the solid salt into water and it dissolves. So we now pick up enthalpy of hydration, delta H hydra. I'll put hydration. It tends to be just hyd, delta H, HYD. So hydrations have got a little bit of extra detail compared to the solution one. So first thing is definition, heat energy change. The heat energy change when 1 mole of. Yeah, well done. Hey, there you go. Heat energy change from 1 mole of, change my color, gaseous ions dissolve in excess water. Dissolve in excess water to form aqueous ions, all under STP. And all to form aqueous. By the way, guys, just to remind you, definitions are horrible. They're grim. Learn an equation. STP, standard temperature and pressure. It's actually just SP technically. Yeah, standard pressure or standard conditions, as you're allowed to put. And the equation, Na plus gaseous going to Na plus aqueous. I want to show you what that now looks like in terms of a diagram, because there are two pictures we need to draw. One is the positive ion. I'm sure I've done this with you guys before. Yeah, we know that water is polar. We know this. Yeah, oxygen slightly negative, hydrogen slightly positive. Well, we are going to form an electrostatic attraction to the positive ion from the oxygen. And we're going to have multiple people do this. This is called a hydrated ion. So but the oxygens will all face towards the sodium. That's the trick here. Because the sodium is plus and the oxygen is, and they love asking you to draw these diagrams because that you can't just throw them together. So we're actually forming during this process. During this process, we form electstat attractions between positive ion and slightly negative oxygen. We are making bonds. If we are making bonds, we know that this process here must be exothermic, and that's the nota bene. Yeah, nota bene, delta H hydras are always underline exothermic because they're making bonds. Now, you will get different levels of exothermic depending on the bonds that you're making. So we can talk about that now, which is kind of neat. So we can make a prediction. I don't want to take that away. I know that the people in the class you see can't pause the video. Because usually I'm just like, pause it if you can't keep up with me. Pause your notes. Amazing. Nikita, let's have a... So, lithium plus versus sodium plus. Which one do you think would give off more energy during hydration? Switch it to ionic radius? High five, virtual high, socially distanced high five. It's amazing. Well done. So lithium ions we know, can I say, very impressed. Lithium ions we know are small, whereas the sodium ions are larger because they have an additional shell. What that means is we realize that ionic bonding, the formation of these electrostatics, are based in two realms: the charge on the ion and the size of the ion. So the lithium 1+, this attraction here is going to be more exothermic. Look at that. This one's going to be more exothermic than the fat sodium ion. So the fat sodium ion is going to be like, yeah, I'm not going to make as good a bonds because I'm bigger and fatter. Not fattest, by the way, not fattest. There we go. But it's just making a smaller, this is just a weaker attraction. We can now compare these two. Yeah. And we know that this one will be stronger. Yeah. It's going to be, therefore, more exothermic. More exo. Yeah. So we can do the same thing for the negative ions, but the picture is subtly different. So if we do the negative ions, so these are the anions. I love a good anion on a hot dog. Really tasty, especially when they're fried. Wow, you guys are rubbish. You know you're meant to be nice to the teachers now. I'm giving you your tags. Whatever. Well, sorry, moving on. So an anion, the Cl- ion, is going to have the exact reverse of the image with water. Damn, this cable's really dodgy. And you can have the reverse image. So the hydrogens now are going to be facing the Cl, there we go, because they're slightly positive and the oxygen is slightly negative. So you reverse the image. I can draw them all the way around if you guys really want me to. Yep. That's a really good question. That's, you know what? It's a really good question. And you know what? I've never had anyone ask it before. That's the first. So, since you've asked such an amazing question, Nikita, how would we go about trying to decide on an answer for that? So, if we were going to attempt to look at the differences between them, how would we do that? What would we compare? So, but hang on, we could try and reduce it. We need a negative ion. Right, so they need to have the same charge and a similar size. Let's look them up. I love, this is good. What an amazing, Nikita, question of 2021 so far. Why do I not have any of my tabs at the bottom? Guys, where are my tabs down here? Does anyone know where my tabs have gone? The problem is, I know the charge density, like, you could work out the charge density by doing m over z, charge over size. But hang on, it's not because that's mass over charge. But in terms of charge over size, you could do. But the problem is, in reality, I wouldn't want to compare a fat 2+ to a small 1+, or a small 1-. Do you know what I mean? I wouldn't want to. I'd want them to have the opposite charges, 1+, 1-, and a similar size. I think that was, so if we do ionic radius periodic table, is it even possible to do it? Let's have a look. Because what we can do is I love, this is one of my favorite tables. This shows you the size of the ions. There you go. Cool. So this table here, please work, just work, please. Don't mess me around. There. Nope, that's ionic. That's there. Right, so the ions are in the center. Is that right? Yes, the ions are in the center. So the gray is the ion and the brown is the normal atom. So we can say that, the metals all shrink, don't they? Makes sense, because you lose electrons, you lose an outer shell, they're going to shrink in size. All the non-metals are growing, ballooning. Yeah. So we need a +1 and a -1 of similar size. 181, 102. So if we go to, oh look, 138 for potassium. No, that doesn't make any sense. Why would that be? Oh yeah, it's ballooned. That's not bad, is it? Guys, what do you think? showing us the 152. The closest comparison we've got is the 138 potassium ion versus the fluoride 133. Would you agree? No, I think that's reasonable. They're the same size. So prediction. What do you think it would be?
It would be the same.
You think they're going to be really similar?
Yes.
By the way, guys, I don't know what's happened here. I think I may have stopped broadcasting because I've lost all my tabs down here.
Oh, no, it's still.
Where are all my things gone?
Oh.
I love my OneNote, but honest to God, this is an absolute. Oh, that's not the right. Oh, nope, that's definitely not the right one. I've lost all my tabs at the bottom. Why? Show toolbar, lock toolbar, show locked. I don't know what I've gone and done. This is an absolute nightmare. There we go. So what we realize is that the lithium it was potassium 1 plus. So K1 plus had an ionic radius of 138, and the fluoride ion, the 1 minus ion, was 133. There is a size difference, but it's only like 5 picometers. So what we now need to do is look up their enthalpies of hydration. And they should be very, very similar. Almost the same. So keyboard. So we need, I should be asking you guys to do this. Fluoride ion hydration enthalpy. Yeah, that'd be great. Hydration enthalpy. I need to add the word enthalpy on the end of that. Enthalpy. Really good question, Nikita. I've never had anyone ask it. It would appear like it would be. Let's do images. There we go. Oh, I've got the potassium 312.
I got 322, negative 322.
For who?
For potassium and fluoride.
Same number.
So, and for one was 322, one is 363 for fluoride.
Hang on. Potassium, I'm getting enthalpy of hydration as 312. Would you agree? How do I? Yes, okay, so that is for potassium, delta H hydra is minus 312. What's the delta H hydra for this guy? Or her? For fluoride. How do I do that funny little swipey thing with multiple hands? Oh. I think this laptop is semi-busted right now.
It's 515.
Is it?
Yeah.
Minus 515. Which
Does that mean I was right?
it suggests it's forming
Twice as many.
not twice.
Almost twice.
It's not almost twice, 66%. But I think, and can I just point out that in reality, like, there is a discrepancy. It would have been if it had been making exactly the same bonds, but due to the slight size difference, I would have expected something like that. But to be 515, that's a big discrepancy. I'd probably say you're right. It's probably making more actual electrostatic attractions than the other one does. Yeah, I think so. Must be. Great question, though. Really clever. Okay, so we now have a definition and understand both of these processes. So what is this whole idea of a cycle? So what we realized was that, by the way, you can put solution cycle. Solution cycle. I teach this through one particular cycle, which they tend to ask more than any other. So the cycle we're going to talk about is, it's usually a silver one that they talk about. Yeah, let's do sodium chloride. Let's keep it easy. So sodium chloride solid can be added to water to form its ions in solution. We also have another option. We can also split sodium chloride into its ions in the process we already now know, thanks to Born-Haber, as the lattice dissociation. Now, this arrow is commonly reversible, depending on the bit of data they happen to give you. So this is data dependent. I'll show you this in a second in a question. But then we get another set of arrows and here are the enthalpy of hydrations. Hydra. So we can create a Hess cycle. Enthalpy of Sol, and this one is either enthalpy of lattice. If they just give you enthalpy of lattice, is it making or breaking, Dana? Well done. Chemists like to make stuff. By standard, it would be making, but then we'll get delta H lattice, maybe. Cool. So we can now create a very simple Hess cycle. Now, the reason why this is useful is because they realized something. They realized for something to be soluble, the question that they ask is soluble, soluble? Question mark? Just go up at the end, intonation. Soluble, and the rule is, and by the way, this is a general rule. Yeah, the rule to answer this question, I should do that in red. Yes, that knows it. I have mentioned it. The sum, damn it, actually that isn't right. I have no idea what you just said there, Dad. Didn't understand a word of what you just said.
So basically asked some question about inverse I have physics chemistry.
Right.
And
Any marks?
I like some marks.
So that's the general rule. In order for something to be dissolved, for something to be soluble, the energy produced in the enthalpy of hydrations, which we know is exothermic. Yeah, this is exo. It gives out heat. We know this. The heat energy coming from the formation of the bonds with the water needs to be greater than the positive breaking of the lattice in the enthalpy of lattice dis. We need to be able to break the bonds. So the diagram here is in order to break, we know that dissolving is a giant structure, a giant ionic lattice, yet held together by the electrostatics. We know this. Yeah, and we've got these electrostatics through and through. If something is going to dissolve and form these ions, we have to break those bonds. We've got to break them. And where does that energy come from? It comes from the formation of the ones to water. Yeah, these ones here, the energy of formation of these guys is used to break it. Does that make sense? So what that means is when anything dissolves in water, it should be exothermic. Should be. However, there are a few which aren't. But the thing is, so this rule is sound. But as a result of this, you get another nota bene. Some dissolving processes are endothermic. Not very endo, but endo. So in that case, why do they happen at all? So C notes on entropy.
So if they're dissolving, if they're endo, they can not be soluble.
Right. So the rule in general is it's probably the most dissolving process will probably be accepted. Not very much. You're talking plus or minus 10. You know, these are small changes. But we do find processes, dissolving processes that are endothermic, they shouldn't exist. Because that process that tells me, it needed more energy to break the lattice than it's getting from the hydrations. So how is this possible? There must be another form of energy. There is. This comes in the form of entropy. Entropy is the energy in chaos. And we will see that in our next topic. Yeah, I will come back to this process in entropy, and we will explain why these exist. Yeah, so we will. See you later notes on entropy. Okay, so what I now want to do is I think at this point we need to put this into context. So, oh no, this is a nightmare. All my tabs have gone because my laptop's crashed. So just whilst I want to do two things. One is to show you exactly what it says on your specification. I think that's very reasonable at this stage. Let's just quickly go to the enthalpy of solution, which is about there. Transition metals might be before it. I just want to really quickly just look through it as the unit 4 notes, which is coming up now. There we go, chemical equilibria, lattice energy, which I think is here. Yeah, there we go. So the bits of interest are define the term enthalpy of solution and hydration of an ion. Be able to use energy cycles to calculate enthalpy of solution using hydration and lattice enthalpies. Understand the effect of ionic charge and radius on the enthalpies of hydrations. Be able to use entropy and enthalpy to explain the solutions. To be able to use entropy and changes of solutions to predict solubility of ionic compounds. We will do that once we get back when we go back to do entropy. But we're covering the first. So what we need to do is now see this in an actual question. So they're usually pretty easy to find, to be fair. This is where my support sheet, it will be super handy. So let's go to Google Drive. Now I'm actually doing this on YouTube just to remind my year 13s here that I have a support sheet that you've all forgotten to use still. Like everyone, it's been a while since we've been doing an awful lot of work on it. So I think a lot of people have just flat out stopped using it. I apparently have completely lost it. Hang on a sec. Yes, I did. Yeah. A2 Chem support. A2 support sheet. Right, there we go. So let's go to topic is energetics. I should call that thermodynamics, really, by the way, guys. I should change that. And let's go to super booklet. It's going to be easier for me to find a solution while on the super booklet. Super booklets are awesome, by the way. I've got 2 of these for each topic, by the way. Oh, there's PIM immediately, perfect dynamic model. There's enthalpy of atoms. There's a Born-Haber. Entropy making an appearance there. Bond enthalpies. I'm just looking for the enthalpy of solution. They're usually pretty easy to spot, partly because they usually give you the equation. There they are. So here's the question. What I'm going to do is I can't snip it because my things have all gone. So stupid. Entropy change for the following. It's actually this one right here. So I'm going to snip that if I find snip on here. Snip. I'm just going to go the long way around here. No. Let's take you. Only 3 marks. Nice and easy. And then go. What the devil? How do I copy this? It's doing something really weird. It needs to be. Why won't it let me take that now? It's drawing lines on it, and I don't. What the devil? Okay, I'll just do it on there. Makes more sense. Right. So, sorry, the connector here is proper shoddy. I hope it's not my laptop. Hang on, guys. It'll come back if I just shove it. There we go. So, the lattice. The first thing you've got to do here, guys, is draw a cycle. So. This is magnesium chloride. So I'm going to take magnesium chloride, solid, and I'm going to instantly turn it into a cycle. Mg, sorry, a habit of writing an A. Mg2 plus aqua plus 2 Cl minus. That's important. In fact, very important, guys. Highlight, recognizing I'm going to get two of them. You'll see why in a second. The next thing I can do is, which one have they given us? Oh, look, lattice formation. So my arrow is going to be making. Formation goes up. So I'm going to make that, damn, sodium, Mg2 plus gas from and 2 Cl minus gases. Right, the hydrations are always going in that direction. Right, now the key thing is the chloride one, which is here, minus 364 must be times by 2 because I'm doing 2 moles of it. That's why you've got to balance it properly. The magnesium one, wow, look how massively exothermic that is. That's insane. And then 202. Right, most important arrows in a Hess cycle. This way equals that way. So I'm now going to go, so this question mark here, yeah, is question mark equals, so this one, this arrow here, this one here is going against me, so minus brackets, minus 2502, and then, so I'm walking around this way, the cycle, yeah, so this one is that one there, and it's against me. This one is with me, because I'm walking in this direction, so then plus brackets, minus 1920, and then this one's also with me as well. Yeah, so that's plus brackets, with plus means with me, minus 364 times 2. Right, run that through my calculator. What's the answer? Negative 146. So that is a very exothermic process. Is it really that high? Is it really? I'm questioning your calculator skills. I'm very surprised at how high that is. Minus brackets, because I don't trust you guys with your, oh, I'm going to flip it in my head. I never like it. No, don't do it. I've told you, Nikita. Don't ever do that. Don't, no. Just no. It is still minus 4. Anyway, we go. So, yeah, that's a very excellent. So if you put magnesium chloride into water, you're going to feel this get warm. That's actually quite an interesting one to see that. But you see the steps I'm running with this. I'm drawing the cycle, adding on the data, making sure it's balanced. And it is a Hess cycle more than it's not a Born-Haber. You can actually draw these as Born-Habers, but I don't like doing it because it sucks. So I tend not to. Let's go back to Windows 10 instead of this guy. Oh, go away. My laptop is in proper state here. So just to mention these questions, I'm going to find another one. So drawing cycles. Yeah, learn one cycle, folks. Learn that cycle and learn to adapt it. That is by far the best way to do this. Learn a cycle that you can then just apply any salt that you have with it. Just remembering to balance it. It's all you really need to do. Okay, so endo and exo. I want to find another one in my super booklet. I have no idea where that's now going to be. Oh dear. I can't move. This is honestly not, my laptop is completely freaked out here. Oh, there it is. Okay, let's find another one. Find another one. Ah, there we are. Use the data to calculate the enthalpy of solution. Exactly the same process, but this time with calcium and fluoride. Again, why are they giving you a 2 plus cation? Because it's going to mean you have to multiply the hydration of the fluoride ion by 2. Would you agree? Exactly the same process, no difference. Oh, check it out. Thermodynamics investigates the substance calcium fluoride dissolving. Give the meaning of each of the following. Enthalpy of lattice formation of calcium fluoride. The heat energy change when 1 mole of calcium fluoride is formed from its gaseous ions. All under standard conditions. Yeah? Does that make sense? By the way, here's the cool bit. Just write the equation for that and then put under standard conditions. You basically get everything. Lol. Shouldn't do that. Do write the equation and then just give a couple of bullet points. Yeah, but the heat energy change when 1 mole of calcium fluoride is formed from its gaseous ions, forming an ionic solid, all under standard conditions. Enthalpy of hydration of a fluoride ion, the heat energy change when 1 mole of gaseous fluoride ions form 1 mole of aqueous fluoride ions when dissolved in excess water, all under standard conditions. Does that make sense? Oh, guys, look at that. Explain the interactions between water molecules and fluoride ions when the fluoride ions become hydrated? Explain. Oh, yes. So, guys, look at that. Oh, that's a great picture, because that one is the diagram of the F minus with the H's towards it. And you get both marks for that picture. Just don't forget your deltas. Yeah, that is the most common mistake there, is that students will just forget the delta bit. But that is this one, but F minus in the center. How cool is that? You don't even have to put a particularly, you don't even have to draw the whole thing. You can actually just draw one molecule of water being attracted to it. Just to also let you know, by the way, that these sometimes, have they ever done it? I'm sure they've done this. That's why I'm thinking about it. So, just to mention that a calcium ion, yeah, small ion, highly charged, high charge density. This actually doesn't just form bonds directly to water molecules in a single layer. You actually get multiple layers. You'll have water molecules in layer 1 with their oxygens pointing towards it. Yeah, they'll have that. But then they'll have another layer of water molecules around it. I think magnesium does about 18 water molecules. Because does that make sense? You're just getting these layers of hydration because there are lots of these waters, because it's just an attraction. So it does happen. And it was asking a question, it was something like, suggest why, it quantified it, it said it, in a student shows a diagram of it making 5 bonds to 5 bonds to 5 water molecules. And then it said, and if you look at the value of that bond, it should be this, but why was it much higher? You just had to state that it will probably be bonding to more water molecules. Does that make sense? Yeah? Yeah? Okay. I'm just mentioning, it was on a multiple choice or something, and I remember having it and being like, what? That's first year degree, that. Sucky.
Ria is confused.
She's confused. Don't worry, Ria. Just ignore everything I'm saying. It's easier. Let's just, guys, all we need to do is just stick to these ones. Yeah. Ria, do you want me to do that? Full screen snip. All you need to do for this one is F minus being attracted, but now we have to flip it so that you're forming the bonds to their H's, because they're slightly positive. Yeah, there's your diagram. Yeah, that's it. If you want it in bullet points, just convert that into bullet points. Huh? Okay. In words, that is the delta positive hydrogen on water molecules, water moles, will be attracted, will form an electrostat attract to the negative anion. Nice and easy. Yeah, not complicated, but that picture there, by the way, this is called an ion, that was weird, an ion dipole interaction. I think it came up on your mock in AS, didn't it? Yeah, you see, I have mentioned this before, but you know, it's fine. Anyway, let's see if I can find another one. I know it's the end of the lesson, guys, but hence why I just think it's nice to do. There's the calcium one that we could look at. I wonder if there's anything of more interest, because there are a couple. The major one is silver, by the way. It might come up now.
What's an ion dipole or
just an ion dipole? Because dipole means an interaction between 2 dipole molecules, whereas this is an ion dipole to 1. Oh, there! No. That's the lattice, predict, theoretical lattice energy. That's the PIM, by the way, of silver. We could work this out. Oh, come on, just give me the question. There. No, calcium again. Damn it! Dad, really quickly, I know that the lesson has 2 minutes left. do me a favor, Dat. Can you look up the enthalpy of hydration for a silver ion? What we're going to do is we're going to prove something. Silver chloride solid, white precipitate. Yeah, test for chloride ions. We know it's not soluble, don't we? Yeah? So, we know that this doesn't happen. Ag plus to Cl minus. This won't happen because we know in this room, this does not happen because we know it's insoluble due to chemical tests. So what we now need to do is just prove why. So can you look up for me? You'll look at the silver ion?
Yes,
Oh, hang on a minute. Hang on. -464. What's the chloride ion?
Well, I have for the formation of AgCl.
Oh, what's the formation?
9-1.
Perfect. 912. And that's going to be forming exothermic. Yeah. Ag, this is AgCl. No, hang on a sec. No, it's coming down. Sorry, I'm making a mess of my cycle. Ag plus gas and Cl minus gas. What's the chloride one? We've already come across that. Wasn't that minus -363? Perfect. So what we can now do is just prove why it's not going to dissolve. Yeah? So we know, most important arrow, this way is the same as this way. So start here. So question mark equals, it's going against me, minus brackets minus 912 plus brackets minus 4. What?
It's
Plus brackets. Someone run that through my calculator, please. What do I get? Go, Nikita, go! It's going to be really endo. There you go. It's really endothermic. Yeah? So, therefore, not soluble. However, would anyone, this is again another horrible question just to mention. Question, how could you get it to dissolve? Well done. Why?
Because it is methods, so they have more activation and they glide more frequently.
You're running, you're annoyingly, okay, Nikita, can I just say, it was a really, really good effort. You dropped into rates. Yeah, but this isn't about rate. I mean, it kind of is. You can talk about it as an activation. Your original answer of activation energy, I liked.
But doesn't that alter the solubility?
It does, but why? Because AgCl solid, we know that state changes are equilibriums. So what we realize is that this process here is endothermic. Oh, look, by the way, penny drop. That was amazing. Love that. Yeah, that's why I teach. Because if you raise the temperature, the equilibrium will shift to lower that temperature by favoring the endothermic reaction. You're adding energy to help break up the lattice. So you push the equilibrium towards the ions in solution. Yeah. What's really going to boggle your brain then is, so hang on a minute, why does temperature just not increase it exponentially? Why does it, you reach a limit? So why? It's purely to do with the number of ions in the solution and it becoming so overcrowded. Eventually you form the saturated solution. A saturated solution, you couldn't look at it in that regard actually. But it's quite fun to look at these things, and it's really nice to get you to understand why solubility increases with temperature. It's because of that equilibrium. Guys, I will end the lesson there. It's been really fun. Really enjoyed it. I've just got to now somehow figure out how to end my recording, even though I've lost all my tabs. Can't wait to restart. Oh, that's not going to help me. Oh no, I can't do it. I can't get back to it. Yes.
So if it was NaCl, if you cool the temperature, then it would be more soluble. Because the full reaction is exothermic.
Now that's a really good point. It should actually reduce the solubility of it. I can't end my YouTube video. I can. I know how to end it. Bye everybody. Shut.